www.nanohub.org. You can follow along with this presentation using printed slides from the NanoHub. Visit www.nanohub.org and download the PDF file containing the slides for this presentation. Print them out and turn each page when you hear the following sound. Enjoy the show.
Recombination generation. This is lecture 13. Now, actually, we have in last 12 lectures, we have done a very important thing. The last lecture was very important because until last lecture, we talked about equilibrium system. That means take a chunk of silicon, put it on your desk in a dark room, let's say, nothing happening, and the system is in equilibrium with the room, same temperature and everything. And we knew how to calculate the number of electrons and holes in that material, right? Where the electrons sit, how they are distributed in terms of Fermi-Dirac statistics for electrons. Now that is all good, of course, but a chunk of silicon sitting on your desk is a good paperweight, but it's not very useful. And what we'll start from today is perturbing this equilibrium of this semiconductor so that electron and hole will flow and we will get something useful out of it. So if you remember very quickly going back to the beginning, that the problem we are interested in is a piece of semiconductor, perhaps uniformly doped, but most likely non-uniformly doped, contacted between two contacts, and we want to find out how much current flows. And one thing we immediately realized from the very beginning, that this will depend on what material it is, how the atoms are arranged. And so that is the first thing we discussed in chapter 1 and 2. And then we immediately said that the number of electrons, the current flow, is proportional to the number of electrons and the velocity. And the number of electrons, how do we calculate that? Well, that is what we did in the last 12 lectures, sort of. Because what we did was use quantum mechanics and this is very important, equilibrium statistical mechanics. That is, we derived Fermi-Dirac statistics without assuming any electric field or potential, right? And in that case, we were able to calculate how many electrons do I have for variable doping and for variable materials. For different materials, we are able to calculate it. Now, this should be clear to you as you do the homework. It will become more clear. The one point I want to make very clearly, that although we have discussed quantum mechanics and statistical mechanics, these are vast subjects. There are courses for it, many courses in Purdue for this, for example, and every other university. But what we'll take out from that, at least for this course, is the only thing is effective masses, which essentially takes the curvature of the EK diagram for each band. And we just had two effective masses because only two bands sort of on the top were involved in conduction process. So two effective masses, that's my quantum mechanics, sort of, and a band gap. Of course, band gap came from quantum mechanics. And from statistical mechanics, well, just the Fermi-Dirac statistics and the temperature, that's all I take. And if I know that, I can calculate electron concentration for arbitrary material. Very powerful concept, actually. Now, of course, next we'll have to calculate the velocity. Once we apply an electric field or a density gradient, if we can somehow calculate the velocity, finally, I have the current. Now, it turns out calculating current, you need a little bit more, because when you want to calculate a current, the semiconductor has to be contacted by two contacts. It will perturb the electron and hole density in a particular way, and the velocity, there will be a corresponding change in the velocity. Now, that is a little bit more complicated. That we'll do in a few classes down. But today, we'll sort of think about a device that has one contact, sort of. And that is a problem in which you have a chunk of silicon and you put a flashlight on it, right? And turn off the flashlight after a little bit and look at how the electron and hole that were generated in response of the light, how they decay as a function of time, because that tells me that when I have a perturbation, remember on the left side, by applying a bias, I am perturbing the equilibrium. And the question is, it tries to restore equilibrium. It wants to go back where it was. And how it does so, these two problems have many analogies. So we'll start from a sort of a quote-unquote single contact problem, in the sense that my flashlight and the photon stream that is coming in is like a single contact, and then I will go to the double and triple and other contacts a little bit later. Now, when you have a semiconductor and you shine light on it or you perturb it some way, then what happens? That the electron and hole numbers changes, right? In the equilibrium, let's say you have 10 to the power 10 per centimeter cube of number at a given temperature, no light and nothing. Now, in this case, all of a sudden, if you perturb it, the electron and hole number is going to change. Now, if you shut the light off, then the electrons and holes are gradually going to find each other, and then they are going to recombine with each other because they don't want to be at the higher carrier concentration. Now, one way they could recombine is an electron in the conduction band. You see, I have shown here a conduction and a valence band. An electron, red electron in the conduction band finds a blank space, the hole, white hole, in the valence band, and then recombine. And when they recombine, they give off a photon. Now, this is a direct recombination that occurs only in a certain subset of material. I will explain in a second. But this is called a direct material, a direct recombination that happens in direct band gap materials generally. Now, one thing you have to notice here, that in real space, how will it look? This is in K space, energy K space. In the real space, what you will see, a red electron is moving around and a white electron hole is moving around. They find each other and then they recombine, a photon comes out. The excess energy the electron had, that comes out as a photon. But this process, you see, is very interesting because these two electrons, and I will show you in a second, the electron and hole must be matched in wavelength. So electron and hole, as soon as they see each other, they don't recombine. In fact, they see each other every 10 to the power minus 13 seconds, about 100 femtoseconds or so. They see each other. Out of a million encounter, they are bouncing off each other, buffeting against each other all the time. But 1 in a million, perhaps, on that order, that is when the wavelength of the red electron is exactly similar, very close to the wavelength of the white hole, and only then they can recombine. You see, that makes it very less probable. It is like listening to a radio station. You see, unless you have the right tuner, you don't really receive the signal. So similarly, the wavelength has to match. Same is the case here. Without this, and that is what makes life difficult here. And that's why this recombination, direct recombination, has a certain rate. We will calculate that a little bit later. Now, many materials, gallium arsenide, indium phosphide, indium antimonide, these do have direct band gap and a significant amount of direct recombination. And lasers and LEDs, these are all work, and it can only work because of this direct recombination can occur. Now, there is something else which doesn't require, is not as restrictive in terms of matching the wavelength of the electrons and holes. And that involves something called an excitonic recombination. So this is another way electron and hole can disappear with each other. Now, these, unlike gallium arsenide, indium phosphide I just talked about, these generally occur in mostly one-dimensional solid. Remember, we talked about one-dimensional semiconductor, two-dimensional semiconductor, and 5 Bravais lattices and 2D, right? Do you remember those? So in mostly one-dimensional one, like a organic transistor or carbon nanotube, in these cases, what happens, the electrons and holes, they have strong Coulomb attraction. So when an electron moves around, there is a bunch of places, there is around it, there is a space in which it has this Coulomb attraction, and as soon as a hole gets into this, even though it doesn't have the same wavelength, they begin to circle each other. and eventually they recombine. So this is a property of a material that has strong Coulomb interaction among the electron and hole, mostly in 1D. So what happens that once they begin to circle each other, they lose a little bit of energy, even though initial wavelength might not have been perfectly matched, and then they give out a photon with wavelength which is a little bit less. Why? Because they lost a little bit energy as they began to circle each other. And in real space, what would it mean? That after the electron and hole have been captured around each other, it's like a binary star, binary, that they begin to circle each other, and eventually, when they have the right wavelength in the right place, they recombine. So this process is one-dimensional semiconductor, very effective, and is an important problem. These days, solar cell is an important topic for research, and in solar cells, this is a very important recombination mechanism. What other way can a semiconductor, can electron and hole disappear? The third process will be called an indirect recombination or trap-assisted recombination. Now, these occurs in indirect bandgap semiconductor. What are indirect bandgap semiconductors? Silicon, germanium, this type of thing. And this is trap-assisted. And you can see that in the energy band diagram, I have drawn a blue line. And the blue line is supposed to indicate the level of traps. Now, what is the distinction between a donor and an acceptor and a trap? Well, no distinction really. But I will show later the ones that are close to the mid gap. Only those can help in this process. If you are close to the conduction band like a donor, or if you are close to the valence band like an acceptor, then this process, they will give away electrons, donors and acceptors, but they cannot help you in terms of recombination. So I will call trap a material that gives a band gap level in the middle of the gap. So for example, copper or gold in silicon, which has a mid gap state, and that's what will be a called trap that can help in this recombination process. That's why you will see in modern microprocessors, all the interconnects are made of copper, right? They copper interconnect. They have multiple layers of interconnections. Now, if you look at them, any picture, go to the website and look at them in picture, then you will see that they are encapsulated by a very thin pinhole-free covering each of the copper interconnects. The reason is even a tiny fraction of the copper, if it could escape and go down in the transistor underneath, your whole IC will die right there. So not even a tiny fraction of coppers are allowed to escape down, because this will immediately kill your transistor because of this recombination process, right? Gold and copper in silicon, but other materials will have different. And the idea is this, that the red electron comes in, gets around the orbit of the trap, right? That's a blue one. In real space, you can see start circling each other. In this case, again, wavelength need not be matched, and it recombines with the holes, because holes does the same thing, and in the process, it releases energy. Now, compared to the direct recombination process, do you think that this rate will be more or less? Because in one case, you see, it now will require the help of a trap. Not only do they have to find each other, they will also have to find a third-party mediator which can help them to recombine. So therefore, this rate is actually very small, on the order of maybe in modern transistors 10 to the power minus 3 seconds to 10 to the power minus 6 seconds. And this is why many of the DRAM memory that you have in computer can actually work and can only be made through indirect bandgap material, not through gallium arsenide. You cannot make a memory out of gallium arsenide per se. We'll explain that later on. I'm just giving you some references. And here, the trap will give away its energy by vibrating, the excess energy it has, by vibrating quite a bit in the beginning and gradually giving away its excess energy to the other atoms nearby, and that's called a phonon. Now, as I said, this is a very important process. We'll spend next 2 classes in fact, just thinking about this particular process. Very important, but the theory is a little bit complicated, so we'll see. Now, there is something called, third thing called, or one of the recombination is called OJ recombination. Now, OJ recombination is slightly different. Remember the problem. My problem is my electron and hole has to have the same wavelength before they can recombine, or they need a trap. But if the density of electrons is very high, then there is an extra mechanism in which the two electrons from the conduction band, shown here as number 2, the red, and the blue, which is difficult to see, one is blue, and then what they do is they bump against each other, and one electron goes down in the valence band, right, and finds the empty hole, recombines there, and the other electron goes up. So in this process, you can see, even though the two initial electrons do not have exactly matched wave vector to the hole, but they can scatter against each other, eventually forcing one to an arbitrary high value and the other one into the hole. This is OJ recombination. In fact, anytime you have a laser, semiconductor laser, indium phosphide, for example, the telecommunication laser that you have, this is the most important recombination process, because in that, doping is so high that electron concentration is extremely high. So they bump against each other all the time, and that forces a recombination. So this is OJ recombination. And what will happen, that the extra electron which went up will gradually lose its energy down to the ground level by sending out heat waves or phonons as a result. Again, the process in real space will be the green one and the red one will scatter against each other and push the red one, let's say, into an empty space, the hole, and the other electron goes up, way up in the conduction band. So this is the OJ process, very important for many, many materials, especially lasers. Now, there is a final one, it's called an impact ionization, which is the reverse of OJ. You can so call it an inverse OJ process in some way, because instead of a recombination, this is like a generation mechanism. Consider the electron 1, red on the top, and consider a energy band diagram that is under electric field. Do you remember that generally we draw it flat? The EC and EV, we generally draw it flat. But as soon as we put a battery on it, did I show you before that it changes the potential, and therefore the electron and hole conduction bands and valence bands, they will change. So here what I'm showing here is an extreme electric field. So you see, although the number 1 starting out has no energy, no kinetic energy, it has a lot of potential energy. Now, if it starts moving, then it will gain a lot of kinetic energy, right, and lose potential energy in the process. But eventually what will happen, that that red electron can scatter off another electron, this time number 2, from the valence band. And once they scatter, it will kick an electron out from the valence band into the conduction band. And in the process, 1 will lose its energy, become 3, right? Because it has to kick somebody out, it had to give that energy. And so 1 becomes 3, and the electron that was in the valence band, that went to number 4, went up. So now I have more electrons in the conduction band and a little bit extra hole in the valence band. Where did electron come in the valence band? Is it not full of holes? Not really, right? Valence band is actually full of electrons, with very tiny amount of holes around, right? Remember, it's below the Fermi level. Below the Fermi level is full of electrons, and only a 1 minus F, that's the holes, only a tiny bit of hole. So in this process, you increase the number of electrons and you increase the number of holes, right? So this is an impact ionization process. Many times you can call it an inverse OJ process, because 2 electrons collided and they eventually went to different places. So therefore, this process is again very important, as we will see. Okay. Now, let me explain to you this statement, strange statement I made, that the electrons and holes have to have the same wavelength before they have to recombine. I mean, that's a strange statement. Why? Before we do that, let me remind you that there are these two types of semiconductors, right? Indirect and direct band gap semiconductor. You know that anytime the top of the valence band and the bottom of the conduction band, the lowest point, are aligned at a particular k, need not be k equals 0, at any particular k, then that's a direct band gap material like gallium arsenide on the right hand panel. And anytime it is not, they are not aligned and they have a different value of k, then they will be on indirect band gap material like silicon, like germanium. And you know that, right? This point you have seen many times. Now, I'm going to focus on gallium arsenide, direct band gap material. Consider my flash lamp is exciting an electron from the valence band to the conduction band in gallium arsenide. And therefore, I have shown a EK diagram that is essentially centered around the same point. You can see, let's say k equals 0. You remember the end of the Brillouin zone is 2 pi over a for silicon. Generally, it's pi over a, but for silicon, for the cubic structure, this is 2 pi over a. And let's say a photon is coming in with a wave vector k photon. This thing is coming in. It kicks the electron up in the conduction band. The red electron up in the conduction band leaves behind a hole. Now, one thing it has to do is to conserve energy, right? Energy conservation. That means whatever was the energy of the electron in the valence band, EV, plus photon, whatever energy it gave it, that must be equal to the electron in the energy of the electron in the conduction band, E sub c. Okay, and the momentum has also to match, right? So HKV is the momentum of the hole. HK photon, well, photon wave vector and photon momentum, and you can see the other one is the electron. So they must balance, momentum balance and energy balance. Now let's calculate the photon wave vector. Not very complicated, right? Because wave vector is given by 2 pi divided by lambda. Why in micron? Because I chose so. My calculation will be easier. So lambda wavelength in micron, let's say. Now, do I know how to calculate the wavelength of a photon? You have done it in chapter 2. That generally it is 1.21 divided by energy of the photon, right? And that's in EV. If you express things in EV, that's in EV. Now, what is the energy of the photon required for an electron to go from the conduction to the valence band? Equal to the band gap, right? On the average, band gap. And band gap is how much? 1 or 2 EV. Let's assume about a 1.21 EV, just for the sake of argument. If I assume that band gap is 1.21 EV, photon energy is 1.21 EV, and so my k photon is 2 pi per micron, 6 per micron. Now think about it, compare that to the end of the Brillouin zone. End of the Brillouin zone is 2 pi over a. And how much is a? Do you remember from the Bravais lattices, how far apart are the atoms? About 4-5 angstrom, right? So you put 5 angstrom in. And do you see how big it is? It is about 10,000 divided by 5, about 2,000. And that's 6. So the end of the Brillouin zone is 10,000, right, per micron, let's say. And that's really like on the order of 1 in 10,000. So if you compare to the end of the Brillouin zone, this will look like a vertical transition. Do you see this? Because the energy of the photon is so large in this case. So therefore, their wave vector, this photon wave vector is actually tiny compared to the Brillouin zone. So therefore, it looks vertical, it is not vertical. But anytime it looks vertical, that means it is negligible. That says that the momentum of the valence electron, HKV, must be approximately equal to the momentum of the valence electron, conduction band electron, HKC. and therefore since kV is equal to kc, their wavelength must match. So anytime a photon is involved, then the wave numbers or wavelengths of the electrons and holes must be matched. And that's what makes it so difficult for recombination. You see, they bump into each other, but most of the time the wavelength don't match. And as a result, they don't recombine. They just bump and there is a scattering and then they go away without recombining. Direct band gap recombination, you see. Okay. Now this is a very important point. You should remember this. Again, once you understand, you will not forget, but make sure that you do. Now what happens in an indirect band gap material? Do I have no hope? Well, I really have no hope of direct recombination because photon is not bringing in much wave vector into the game. It gives you a lot of energy, but not much wave vector. So therefore, there is no way that it is going to take an electron from the valence band in indirect band gap material and pump it into the conduction band because the wave vectors are so different. Right? Do you remember in silicon that the bottom of the conduction band is almost to the edge of the Brillouin zone and the bottom of the valence band, well, in the gamma point, in the zone center. So therefore, so different, no hope that a photon will typically do it. Again, but in this case, a phonon can do it. Phonon is a lattice vibration, so it can do it. Again, I write the energy conservation and the momentum conservation. Again, I try to calculate the wave vector for the phonon. I will not explain this very much, but you can see the wavelength of phonon is the wavelength of a sound wave, right? Because phonon essentially sound wave moves by moving the atoms around, right? And so essentially you can calculate the wavelength lambda by the velocity of the sound and the phonon energy. Phonon energy is small, but the velocity of sound is also very small compared to velocity of light. How much is it? You know, it's about 1,000 meters per second, right? Is that right? Velocity of sound, approximately. And what is the velocity of light? 10 to the power 8 or so, right? So huge difference, 5 orders of magnitude difference. So you can see why phonon wavelength. Phonon essentially these atoms move up and down, bob up and down. So you can see the wavelength that you can fit can be huge. And as a result, that is actually almost equal to the Brillouin zone edge. And so when a phonon is involved, it doesn't have much energy, but it can give you a lot of wave vector, changes wave vector, and in the process, it can help recombination process. So it's indirect band gap recombination. By the way, I'm writing this word BZ on the bottom. BZ stands for Brillouin zone. So it takes a little bit to write. So remember that this word means end of the Brillouin zone, 2 pi over A. Now, how does traps help? Well, if you think about a trap has a dimension of A. Trap is a impurity atom, right? Foreign atom. You have a bunch of green, deep green silicon, and you have one light green impurity atom sitting there. And what it does, that the wave vector of the trap, when the trap is moving up and down, is on the order of 2 pi over A. And what it helps is that the trap level is right there, shown here in the energy band diagram as a small red line. And what the trap does, it provides a lot of wave vector so that the electron from that bottom of the conduction band can move to the trap, right? And once it is there, it is perfectly aligned with the valence band. And so now when the right hole comes in, it just drops in. And then in the process, it recombines. So that is how the indirect band gap recombination occurs. You can immediately see physically why indirect band gap recombination is so difficult, right? It needs to be first captured by a trap. If you don't have a trap, it's not going to recombine at all. Once it has a trap, then it has to wait for a hole to come along. And so therefore, this is on the order of a millisecond to a microsecond for this recombination to occur. How would you increase it if you wanted to shorten it? Just increase the number of traps, right? And we'll see a transistor or a diode that diode will show how this increase actually help the performance of a diode later on. Now let me give you some, so that's all. These are various processes by which extra electron can recombine with extra hole. This is not rocket science, very simple. Now let me explain a concept which is a very important concept in preparation of derivation of the recombination generation formula, the overall formula that we will do in the next class. I want to describe a few concepts, and this you need to understand very clearly. Steady state and transient response. Consider that we have a room, the yellow room, and let's say this room, this looks like yellow here, and whatever the temperature of that room is, and my computer, and that is supposed to be a thermometer on the right hand side, it has a certain temperature, and my computer in green is sitting there in equilibrium with the room. Now if I change the temperature of the room all on a sudden, so let's say the temperature of the room is changing, then the electron device has to go to now a new equilibrium point. Do you remember in the last class we said as you increase the temperature, the number of electrons changes from the freeze out to intrinsic to the extrinsic region? Do you remember? That means that every temperature the electron concentration is actually different. So all on a sudden if you increase the temperature, then the number of electrons might change, right, from one value to another. So what is going to happen that, let's say in the equilibrium case, this was your electron and hole concentration. As you increase the temperature all on a sudden, it will go to a new value. Electron and hole will go to a new value. So this is a transient response, but eventually if you keep the temperature the same, eventually it will reach to a steady state. And how is this different from transient? Well, here you allowed it to reach to a equilibrium value, but if you turn the temperature on and off, the thermostat on and off all the time, then of course what will happen that it will never be able to reach a level. It will go up and then it will go down, go up and go down. So that will be a transient response. Now I want you to understand this concept very well because I'll show you through a series of cartoons that what these concepts exactly mean. Now one thing I want to first point out is the notion of equilibrium and the notion of a detailed balance. Equilibrium, what is equilibrium? Many times a bunch of silicon, a chunk of silicon sitting on your desk. It looks like nothing is happening. Not really. Inside the semiconductor, a violent storm is raging. Electrons are bouncing off each other every 100 femtoseconds, going in their way, and they are redistributing energy, redistributing wavelength. They are in a violent motion everywhere. However, if you look at individual processes, the number of electrons at a given time in the conduction band, you will see 2 electrons going to the valence band, 2 electrons coming from the valence band in the conduction band. So if you just look at the number of electrons at a given time, it looks like it's 10 to the power 10. But this is not the same 10 to the power 10 if you could tag the electrons. Not the same 10 to the power 10 that it was there 2 seconds ago. It's constantly changing from valence band to conduction band, redistributing its energy, but the rate is the same. Going in and out is the same, and therefore that is called equilibrium. Equilibrium doesn't mean that everybody is sitting in their place. If everybody sat in their place, there will be no Fermi-Dirac statistics. Remember Fermi-Dirac statistics? They had to change their position, go through all the combination that you could allow. Now, if you just freeze them in a given place, the number of permutation will be 1. No Fermi-Dirac statistics. Fermi-Dirac statistics implies that electrons are violently moving around each other and redistributing their energy all the time. Okay, so equilibrium is really a very active place, and one way to think about equilibrium, think about USA here to be the device, and China, Mexico and India to be various other energy states. This is equilibrium. It means from Mexico to USA, let's say 2% coming in, and from USA to Mexico, 2% going out. So if you look at USA, it's not the same person, same set of people, static, but the number is the same. And you see, between any pair of states, the rates are exactly balanced. So from India, 4% per day, let's say, in and out. So this is called detailed balance. Detailed balance means individually each pair of states balanced among each other. You don't even have to look to other things. This is detailed balance, and it is a property of equilibrium and equilibrium only. Okay, so this, I have a few words here. You can read it later on, but the point is, as I said, Fermi-Dirac statistics, Bose-Einstein distribution relies on this notion of detailed balance. Okay. Now, what is steady state? Well, steady state is the following. Consider the figure on the right hand side, and let me walk you through. The number of people coming from Mexico to USA is 3, but the other way around is 2. So they are not individually balanced. You see, they are not individually balanced. And that's, let's say, the same for all other things. You see that the rates in and out are not individually balanced. That means detailed balance has been broken, right? But look at the sum. 3 people coming in from Mexico, 4 from China, let's say, and 5 from India. How many total? 12. How many going out? I also have 2, 6, and 4. 12 going out. So if I was just focusing on the USA, that energy level, then I will see no change in number. Although to individual states, the numbers are changing, the rates are very, very different. This is steady state. It means for the relevant energy state that I'm interested in, no net change in number, but that doesn't mean that every rate is individually balanced. No detailed balance here in steady state. So if you look at this side by side, this is, the middle one is transient. So first one is, do you see, first one is detailed balance, means steady state, right? Means equilibrium. The second one is transient, and let's compare it to the third one, and let me, so the last one is steady state, where 12 in, 12 out, population is same and independent of time. But think about the one in the middle. In the transient state, I have 2, 3, and 5, 10 coming in, 3, 5, and 4, 12 going out. That means in the transient phase, neither detailed balance is valid, not integrated flux is valid. None of them are valid because this is changing all around. Now, if you take the whole thing as a whole, meaning take the magenta, Mexico, China, India, USA, all thing together, since electron can neither be created or destroyed, the whole thing globally, of course, is in equilibrium, in steady state, the whole thing globally. But if you look at individually, they are not. So these three things has to be cleanly understood because we will be using many of this in later derivation. Okay, we'll get started today on the recombination generation formula, but we will actually do the dirty work in the next class. But let me explain to you, and we will focus on this one. This is the most difficult one. The others really require one line to derive. So we'll do the hard work here, but let's get started. I'm talking about trap-assisted indirect recombination, silicon and in germanium, right? And then we'll see. Assume that I have a few traps here. The total number of traps, mid-gap levels, is, let's say here 6, blue plus red. Blue ones are the ones that has already captured an electron. It's full. And the red ones are ones that is empty. So the trap is empty. Remember, just like donut, sometimes it can be empty, sometimes it can be full. Similarly, here I am saying anytime they are full, this is n small n sub t, and anytime they are empty, then that's the red ones. That's the empty traps. Now let's think about an electron. The black one on the left is an electron, and the white open circle is a hole. So first thing is that if you start here, start watching the movie from here, you will see that the electron is sort of bounced back and forth, and it will then get captured in one of the empty traps, right? Okay. Now why is the electron doing that? Who is actually bouncing it around? Do you remember this green thing that in the background that I have drawn is actually not a uniform material. These are all the atoms are sitting there. All the atoms are sitting there. I have drawn it as a flat space, but the atoms are sitting there, and remember, they are actually jiggling in temperature. And so when the black electron goes around, when it meets a right atom, it might be scattered and goes in another direction, and it scatters in various ways, eventually meeting the red trap, which is the empty trap. Okay, so if you have that, after that electron has been captured, how many traps do you have now? Well, I still have 6, because I'm not destroying any trap. I just got one trap which was initially empty, red one, converted into on the right hand top side into a blue circle, which means I have that full. So therefore now I have 4 full traps and 2 empty traps. That's it. So but still it's 6. Number has changed between NT and PT, right? A little bit later, let's say the hole gets captured by one that had an electron. So because this white hole got captured in a blue trap that had an extra electron, so it got captured. So therefore I am returning to the same space I was before, 3 electron and 3 hole. But in the process, look at what the fate of the electron and hole. They have disappeared from the picture. So you see what the trap did was assist in the process of finding electron and hole, temporarily sort of storing the electron so that a hole can come later on and find it and disappear in the process. So this is the mechanics of indirect band gap transition. Okay. Now, to get started on this, we have to calculate the rate at which the electrons and holes disappear. So let me just get started on that derivation. Let's say I'm thinking about electrons, d and dt. Per unit time, how many electrons disappear? Now, do you agree with the formula on the right hand side? The figure on the left hand side, the green figure, is a projection on one-dimensional space. Actually, it's a 3-dimensional material. So on the right hand side, I have recopied it, but this time drawn it in 3 dimension. And you can see again I have drawn the 3 red circles and the 3 blue circles. Now this electron, the black electron, essentially is moving with a velocity, let's say v thermal, and I'll explain what that in a second. And in a time t, it will go v thermal multiplied by t. That's one side of the box. The other side of the box is A, the cross-sectional area. So A multiplied by VTHD, this is the volume of the box. The first 2 terms is the volume of the box. Now, if I didn't have any trap or empty trap to capture this electron, it doesn't matter how big the box is. So the P sub T or P sub T is the number of red empty traps available for capture. And sigma n says how big the red is. If the red is tiny, right, it will not be able to capture much. But if the red is a big circle, and I'll explain what that means, then it will be able to capture the electrons very easily. And I have to divide A by T because I want to. And by the way, the whole process is proportional to the number of electrons, of course. If I have more electrons, more recombination. No rocket science again, very simple. And I can, most of the other things are constant. So I can call it a capture constant C sub n, put it in here, and I'll explain what it means in a second. And you can see it's proportional to the number of empty traps and proportional to the number of electrons. What is the solution of this equation? d and dt, this is an exponential, right? Do you see immediately that if you shine light and then turn off your torchlight, then as a function of time, the extra electron and hole will gradually decay off almost exponentially. Of course, not exactly exponential, because p sub t, as the electrons are recombining, the p sub t itself might change, and therefore may not be exactly an exponential, but you can see this is what the result is eventually going to be. What is that V thermal? Well, V thermal is the average energy by which the electrons move around, and you know half mv squared is 3/2 kT. This is from the statistical mechanics, we know that that's the case. If it is three-dimensional solid, 3/2 kT. One-dimensional solid, half kT. And two-dimensional solid, graphene, kT, right? So from that, we should be able to calculate the thermal velocity. Thermal velocity is on the order of 10 to the power 7 centimeter per second. So that's about all semiconductors have about the same number, 10 to the power 7 centimeter per second. Now, this capture cross section, I will discuss this and end there. The capture cross section is a geometrical thing. Assume that you have a sphere and somebody is throwing dart at your sphere, right? So there's a sphere sitting, somebody is throwing dart. Now, what is the probability that the dart will hit the sphere? Depends on how big the radius is, right? And not general radius, not 4/3 pi r cubed, because for the person who is throwing the dart, it is the cross section that matters, pi r naught square. Now, what is the typical diameter of a trap? You know, trap replaced one of the atoms in the lattice, and the atom spacing was how much? About 5 angstrom, right? And so r naught, without doing any calculation, you can estimate on the order of 5 angstrom. I have a little circle, the atom is about to capture electrons. Okay, so if I put r naught equals on the order of 5 to 10 nanometer, 5 to 10 angstrom, then you can immediately realize that this value is going to be on the order of 10 to the power minus 14 centimeters square. Do you see that? 10 angstrom, 10 to the power minus 7 centimeter, r square, 10 to the power minus 14 centimeters, right? Okay, so in fact, if electron is trying to come in and get captured in one of the red empty traps, the capture cross section is going to be on the order of 10 to the power 14 to 10 to the power minus 16. Depends on the exact material, but on that order. Okay, now this is zinc capture model in silicon. That means how zinc behaves. Copper will have a slightly different value and gold will have a slightly different value. So the electron comes in and they get captured in this one, but once they get captured, it doesn't want a second electron to be captured in that anymore, right? Because it already has one. Now, if you want a second electron to get into the first trap, which already has one, it doesn't want anymore, you will really have to give it a lot of energy, or if its effective cross section is much smaller now, because it doesn't want to capture anymore. That is 10 to the power 18 minus 18. And if it already has 2, if you try to put a third one in there, oh, it's not buying anymore, it is full. So its capture is sort of trying to disappear itself from the view of the electrons. It doesn't want anymore. And so therefore it becomes smaller and smaller cross section, and they do not participate in the recombination process, you see. So they disappear. On the other hand, as an electron, let's say it has captured a certain number of electrons, for the hole it is very attractive because it is a charged thing, and therefore a hole can easily capture. So look at this number. So as soon as it has captured an electron, for the second electron, E2, the cross section is small. It doesn't want a second electron, but it wants a hole. And that's, in that case, for the first hole, you can see that it is 10 to the power minus 15, right? It's much larger, right? Now assume that it has, for some reason, captured 2 electrons. Now then, it is even better for the holes, because it has 2 electrons. It really wants a hole. And so therefore, the hole will come in, and essentially it will have a huge cross section for the hole, right? And this is a zinc It's a mid-gap state in silicon. So that's the model for gold and copper. You will have similar types of models. It's done very well in your textbook. Take a look at this particular picture. It's done in a form of a table. Try to understand the table, because remembering these things, it's not very helpful. You have to understand them physically so that it stays with you regardless of where you go, independent of the textbook you use. And this has a name called Cascade Model for Capture. It was first done in 1968 or so, and the person who did it, Lax, I actually worked with him for a few years when I was in Bell Labs. Beautiful, beautiful theory, actually. I cannot do that here. It's an introductory course, but in some other course maybe. Okay, let me end. So the first thing I wanted to say was that once you perturb equilibrium, restoration of the equilibrium can happen through many channels. Direct recombination, OJ, right? OJ recombination, trap-assisted recombination. Some are more important in some solid and others in other solids, other materials. So we'll have to really know them all, but apply them carefully. Now, the one thing I also mentioned, spend some time, the direct recombination is photon assisted. Photon has actually very little wave vector. That's why when you stand in front of your mirror in the morning, the mirror doesn't start to rotate, hopefully, because although the photons are bouncing off the mirror, but hopefully they contain such a small amount of momentum that in order to see the momentum, you'll have to have a tiny mirrors suspended at a very, very low temperature. And then you can see that, of course, it jiggles around, right? The photons. Photon does have a wave vector, very small. Phonon, on the other hand, has a huge wave vector, no energy. So that's the distinction, indirect recombination. And I tried to explain to you the notion of an equilibrium. Lots of things are happening in equilibrium. It's not sitting there. And that is the origin of Fermi-Dirac statistics and steady state and transient dynamics. You need to understand this clearly so that when we apply them, you have no questions about their relevance or appropriateness. Okay? Thank you.